Here is the overview of the computer system. In this computer system, or a computing stack, you have multiple layers from the software to hardware. First, you need to have some applications to achieve some goal. For example, you want to train a neural network, and then you need to have some algorithm help you to achieve that goal. For example, you can use different training algorithm to train a neural network. And then you can implement that algorithm by different languages, Python or C. These high-level language, even the C is a high-level language, will be translated to some assembly language. These assembly language will be implemented by some instruction set architecture. If you run them on GPU, then it will be assembly to some GPU assembly language. If you run them on CPU, they will be translated into some x86 languages. Even you run everything on CPU, you have a different microarchitecture. For example, you can spend $1,000 to buy a CPU. Potentially, it will have a very large cache or a lot of core, or you can even run that on your mobile phone, which has a smaller cache and maybe only 2 cores. And the core will be implemented by different circuits. And you can use different devices, of course, different devices to implement the circuit. For example, now you can use 4 nanometer process technology transistor to implement the circuit, or 16 nanometer. They have a different performance and a different power consumption. Well, all the computer system from your mobile phone to some supercomputer servers actually have the same abstraction. If you do not care about latency or memory, all the computing devices here potentially can do the same thing. For example, if you want to run some LeanPack application, so of course it will be very fast. But if you do not care about speed, you can also run that. They can achieve the same goal because all the computer systems are actually Turing machine. They have the same abstract model like this. All the computers have the capability of reading and writing some symbols on an infinite tape. They have state transitions based on the current state and symbols. The symbol indicate the input. So every computation, every operation is actually implemented by some Turing machine. For example, addition or multiplication. These are the read. These are all. And you can write. And between the input and output, which can help you to implement some operation. The function of the Turing machine can you can use the Turing machine to implement a lot of functions. not only the addition, multiplication. Any complex function can be implemented by Turing machine. So if we call this function as U, U is a programmable. A neural network is also a Turing machine. And the function is programmed by the instructions. And the instructions are part of the input data. So your computer is exactly a because you can do the programming on your computer to implement a certain types of function. But this is just theoretically you all Turing machine, but in fact, to implement the same function, different computer may have different latency and different power consumption. So in order to practically solve some problem, we need to consider these factors. Although you can achieve that goal or achieve that function, but you also need to consider the time and latency, cost, and power consumption. Use your mobile phone to run Linpack is not a good idea because it will be very slow. So when we try to implement some function on the computer, we need to consider these issues. First, we need to consider the problem itself. So what's the goal of your? And then you need to design algorithm to implement that function to achieve the problem goal. And when you try to implement that function, you have different algorithms, and you can use different bit structures. And you can use different language. C or assembly language. And then you can compile your application written by some high-level language. Assembly language from the instruction set. For example, a GPU or a CPU. So here we have 4 layers. Between 2 layers, 2 consecutive layers, we may need to make some decisions, design decisions. And each decision will give you different latency, cost, and power consumption, of course. For example, if your problem is, again, train some neural network, you can use SDD or Adam optimizer to train your neural network. These are different algorithms, and you can use C to implement, for example, SDD algorithm. And you can program your Python C on a GPU or a CPU. So each layer you have different options. And a different option will give you different trade-offs between the power consumption, latency, and the cost. Even you decide, for example, run that on a GPU, you still can choose different GPUs. For example, you can use CUDA 11 or CUDA 10 or CUDA 9 on different GPU microarchitectures. The GPU microarchitecture, includes some basic parameter of the GPU. For example, the CUDA core number, the register file size, the cache size on the GPU. And then even for the same microarchitecture, implemented by different circuits, and which can be fabricated by different process technology, 4 nanometer, 8 nanometer, and different design options will give you different latency, different power consumption. So in order to fully optimize a application, we need to make decisions at each layer in the computing system. Then we need to consider these issues. The problem, the algorithm, which language you will use, and the instruction set. And then the microarchitecture, and then the logic circuits, then the devices. So you can see that at each layer, you have different options. And this is a huge design space. When we put the design space into a picture, we have something like this. This example is to solve a system of equations. You have different algorithms. Different algorithms can help you to achieve the same goal. And even you select this algorithm, you can implement that in different language. Even you select this language, you can compile this language on different micro instruction sets. And even you select the most common one, the Intel x86, you have a different CPU, AMD, Intel. And then you can use different circuits to implement the same CPU. And the circuit can be fabricated by different process technology. And all these operations and eventually from the problem to the devices will give you different cost, performance, and the power consumption. So for example, the option one is from here to here. Maybe you have another option from this from there to this bottom level. And these two passes will give you different performance, of course, and different power consumption. So before you try to solve the problem, you need to consider all these factors. You need to answer this question. Again, take the training algorithm as one example. If you decide to train a neural network, very simple option for you is that whether you need to do that on GPU or CPU. Clearly, you need to select the GPU because the GPU is highly optimized for the matrix operation. by selecting the GPU, you can greatly reduce the latency, training latency by maybe 1,000 times. And then in this lecture, we will talk about the lowest level of the data representation, which is a bits. So we use 0 and 1 in the computer system to represent a number. So this is the binary data. And we use the voltage to represent 1 and 0. This is because in the binary system, it's easier for the circuit to implement these binary systems compared to the decimal number system. So the simplest way to represent the data, we can use even the combo to represent the data. For example, if you have something like this, this is and this is a 1 here. But in the digital system, we use voltage to represent the data. And of course, in the real system, everything is analog. So we give a range to the 0 and a range to 1. So we don't use this range. If some voltage fall into this, then it's not all 0. So by 2 states, voltage states, we can represent a single bit. And 2 bits are represented by 4 states. In another word, we can use 2 to n states to represent n bits. Now we only have the raw binary bits. How can we represent numbers, image, text, sound by these binary bits? Then we need a different data type. The simplest data type is an unsigned number, where you only have a 0 and a positive number. No negative number in this unsigned number system. This unsigned integer system. So this is how we represent a number decimal. So we have 309 from the most significant bit to the least significant. Similar to this system, in the binary system, we also have the most significant. But here, instead of 0, each bit represents, for example, this bit is 222, and this bit is 220. They have a similar configuration, but each number here have a different basis. The base here is 2, but the base here is 10. Here is a truth table for the 3 bits unsigned integer number. Because we have 3 bits, then we can represent 2 to 3 numbers, 8 numbers from 0 to 7. And all the rows here are all the combination of these 3 bits. Each bit can be 0 or 1. By the unsigned integer, we can do base 2 addition, which is also similar to the base 10. For example, if we want to we can do that. First, we can start from the least significant here. The sum of 0 and 1 is 1. And then the next bit, 1 plus 1. The sum is 0. And we also have a carry here. So the carry is 1, and then the number here is 0, and another number is here is 0. So the result here is 1. So in this way, we can do the subtraction, multiplication, and even the division. So this is the unsigned integer here. The next step is the signed integer. Compared to the unsigned integer, we need 1 extra bit to represent the sign. We use the most significant bit to do that. So if the most significant bit is 0, it's a positive number. This is a positive 5. If the most significant bit is 1, then this is a negative number, minus 5. We can also have the ones complement format, which is we keep the most significant unchanged, and then flip all the other bits. Here we have 0, 1, 0, 1. In the ones complement form, we have 1, 0, 1, 0. It's also a minus 5. But in the ones complement format, we have a problem. The problem is that we have 2 zeros, a positive 0 and a negative 0. So which means that if we have a 3 bits here, if we use these 3 bits to represent a unsigned integer, then we can use these 3 to represent 8 unsigned integer here. If we use the one complement form to represent the signed integer, then we have a positive 0 and a negative 0 here. So by 3 bits, we can only represent 7 numbers because we have 2 zeros. So in order to remove a 0, we need a 2's complement. The 2's complement representation is simple. You can just add 1 on the 1's complement form. For example, in the 1's complement form, this is minus 5. Which is the most significant bit is 1 because it's a minus 5. And then we have 1, 0, 1, 0. if we use two's complement representation to represent this -5, the most significant integer is still 1 because it's -5. And then instead of 1, 0, 1, 0, we add 1 here. Then this is the two's complement. By the two's complement representation, we can directly use the adder to compute the subtraction. 5 minus 5 is equivalent to 5 plus -5. And then you can directly do the addition here. For example, the 1 plus 1. Sum is a 0, and then you have a carry here. When you have a carry, this is a 0, this is 1. Sum is still 0, you have another carry here. And then you can do the computation like this. Eventually, this result is exactly the result of the function. So the subtraction is converted to a normal addition. So the two's complement representation is very important because it can help you to compute the subtraction. So if your number is a positive or 0, then the two's complement form of this number is exactly the same as the unsigned number. If your number is a negative number, then you need to convert this number to the 1's complement first, and then plus a 1. So here is the example. If you want to represent -5, you need to compute the 1's complement form. Because this -5 is the most significant digit is 1, and then you invert. Yes. This is. You can do the same thing. This is another, example to help you to convert a number to its two's complement form. Convert this number to the 1's complement form first, and then plus 1. So in the two's complement signed number system, the most significant bit is the sum bit. 1 indicates that this is an negative number. 0 is positive number. 0. Here we have 4 bits. 1, 2, 3, 4 bits. By 4 bits, we can represent 16 numbers. Because we have a 2 to 4, which is a 16. And in this two's complement signed integer system, we exactly have 16 numbers here from 0 to 7, from -8 to -1. And in this system, we don't have the -0 and +0 problem anymore. Now we have a two commonly used number system. The first one is the decimal number system, and then we have a binary number system. How can we convert them? The conversion between them is very simple. You can do this like this. So this bit represents 2 to 0, 2 to 1, 2 to 2, 2 to 3. Because we only have 3 ones here, we just need to pick up the corresponding position. So this one, this is 2 to 3. This one 2 to 5, and this one 2 to 6. We just sum them together. And then we have the decimal of this number. So this is the binary number of. This is the decimal number of x. And we can summarize this by this table. In this table, n is the bit number. For example, this is n0, n1, n2. And then this 2 to n represents 2 to 0, 2 to 1, 2 to 2. And then you have 2 to 10 here. So when I give you this table, you can easily. So in this way, you can convert a number, a binary number, to its equivalent decimal number. Here is another example. Again, the first part is you have a positive. Why? Because the most significant bit is 0. And this is 2 to 0, 2 to 1, 2 to 2. You have all these. You have 2 to 3, you have 2 to 4, you have 2 to 5. And then you just need to sum them together. So this one is more complex. Why? Because why this is a negative number? Because the most significant bit is 1. So this is the two's complement format of X. The first thing you need to do is to get the value of negative X. Because this is a two's complement, you can now simply remove this sign bit. This is not X. In order to have the minus X, you need to do this. This is the original X. You can remove the sign bit and then minus 1. Minus 1 can help you to get the ones complement form. And then invert. So this is the minus X. You can see this is the minus X. When you have the minus X, you can use the same method like this to compute it. And in this way, you can have 26. So the X is a minus 26. When you have a negative number and the negative number represented by some two's complement form. You compute one's complement form first, and then convert the number. So this is all for how to convert a binary number to its decimal form. And this slide indicates how to convert a decimal number to its binary representation. For example, the x is 104. Decimal. This is a decimal number. You can use this number divided by 2. The result is 52. The remainder is 0. So you can write out this remainder as the 0, bit 0. You can keep using this. You have the result. And eventually, when you have a no, when the result is 0, you can stop. So this is the bit 0, bit 1, bit 0, bit 1, and you can have that x. Another way to do that is do the subtraction. Because you are familiar with this table. And x is 104. It's smaller than this 128. So you cannot minus this one, because this is not large enough. You will start from 65. And then 22, and then 8, until you have a 0 here. And only the bit 6, 5, 3 are 1. Personally, I prefer the first one. You can always use a number divided by 2 and record the remainder. So now you can convert a binary to its decimal representation and the decimal number to its binary representation. And you can represent unsigned integer, signed. Particularly if the number is an active number, you can have 2 complement representations. The next step is to do more operations, arithmetic operation, and the logic operation on these numbers. Back to the addition example. When you try to do some subtraction, you just convert second number into its 2 complement form. A number minus a minus b is equivalent to a plus minus b. In this way, you can compute a subtraction. So here is the example of a subtraction. First, you convert this number to its 2's complement form. and then just do the addition here. So the original sign here is subtraction. When you after you convert this number to a two-dimensional form, you can change this to a plus. A minus B is equals to A plus minus. Sometimes you need to do some sign extension. For example, if you have more bits, you need to convert these 4 bits to its 8-bit form. So if this number is a positive, yes, positive, you just need to write all zeros here. It's still a positive form. However, if this number is negative, if you write all zeros into its most significant bits, these 4 most significant bits, this is not right. Why? Because this number is actually a positive number. The significant bit of this is a 0. So instead of writing all zeros here, you need to write all ones. This is the real negative form. In this number, most significant bit is 1. So it's a negative number. This is particularly useful when you try to convert some variable in your C system. For example, if you want to convert a number from a short to integer, int, this is what will happen. The compiler will automatically do this for you. Then we have the overflow problem. The overflow problem means that when you try to sum 2 positive numbers, the result can be negative. This is what will happen in the first example. Positive 8 plus positive 9. In this particular example, is negative 50. Why is a negative? Because the most significant bit here is a1. So the result is a negative number. Why you have such problem? Because here you only have 5 bits, and the result of this operation is 17. Positive 17. You cannot use 5 bits to represent a positive 17. The maximum these 5 bits can represent is 16. Then in this case, you will have an overflow problem. Another overflow problem is when you have a negative 8, you try to plus a negative 9. The result will be negative 17. But when you do this, you have a positive 50. Again, this is a wrong number. Why it's positive? Because the most significant bit is a 0. Why you also have an overflow problem here, because by 5 bits you cannot represent negative 17. The smallest number it can represent is negative 16. So by a limited number of bits, you cannot represent a too large or too small numbers. You can only represent a range of numbers. Any number for out of this range will suffer from this overflow problem. How to solve this overflow problem? You need to add more bits here. You can use 6 bits to do this, or 7 bits. Another type, besides the arithmetic operation, another type is a logic operation. In the logic operation, the operands are 1 or 0. And then we have A and B, A or B, and not A. These are three simplest logic operations. A and B are 1-bit variable, 0 or 1. And then you can perform these three types of operations. And these are the truth table for these three operations. How about multiple bits operands? For example, in this example, one operand is 8 bits. Then you just need to do the AND operation. For example, from the least significant bit, 1 and 1 is 1, 0 and 1 is 0. So there's no carry. Okay, so each bit operation on each bit is independent. You will have the same thing for all and for not. Besides the base 2, another commonly used number system is a hex number system in the computer system, of course. In the hex system, we have from 0. In binary system, we only have 0 and 1, but in the hex, we have 0. And then the 15, as indicated 15. Which means that if we convert a binary number to its hex format, we can have a more compact form, because each 4 bits can be represented. So here is one example. The conversion from a binary number to hex number is very simple. You just convert each 4 bits to its hex. This is a 7. This is the D. How to convert these 4 bits to this one? You can use the same algorithm, which convert the binary to the decimal number. So because you only have 4 bits here, this is 220, 221, 222, 223. For this particular region, then this is a 7. This is 13. 13 is the key. Now we can handle all the integers. How about the dot, the fraction? We have a different method to do that. The simplest one is a fixed point number. We just enforce that we have 3 fractions. And both A and B have the last 3 bits, the least significant 3 bits are the fractions. And then we can align by this dot and then do addition, subtraction. This is very easy. You don't need to change too much from the integer. But this method is not flexible. Why? Because A may require 5 for the fraction. B may only require 1 bit for the fraction. So it's not flexible. Then we need a so-called floating point variable. The standard of floating point is enforced by IEEE. IEEE has some standard on this floating point number. The 32-bit is a so-called single precision floating point number, which is represented by float in C language. And you also have 64-bit floating point number, which is represented by double. So basically, this is the format of a single precision floating point number. 1 bit for sign, 8 bit for exponent, and the 32 as 23 bits for the fraction. And you can use these equations to compute the value of that number n. I will present one example. For example, this number. The sum bit here is 1, which means that this is a negative. And then the exponent is this one. When we convert this number to its decimal, it's this value. Then we have the fraction. This is the fraction. For the fraction, it's similar to the integer. So for this bit, we call it 2 to 0. For this bit, we call it 2 to minus 1, and then 2 to minus 2, and 2 to minus 2. This from here we have 2 to 1, 2 to 2. Because this is a 2 to minus 1, we have a 0.5 here. This is 0.5. We know the S, E, and F. We can use this equation to compute the value. And then we have the value of this one. So compared to the fixed point, this floating point can represent a larger range by the same bits. The regular two's complement representation does not work for this floating point. Why? Because you have to normalize them. You cannot directly add two. You have to normalize, make sure they have the same, then do the computation. By the binary bits, you can also represent text. The simplest one is ASIC2. Each character here is a 7-bit. The relationship between a decimal digit and its ASIC2 code is that this is 1 and this is 0. I believe the relationship is a number plus 30 equals to its ASIC code for these numbers here. And the difference between a upper bound letter and its lowercase letter is uppercase letter and its lowercase letter is this. There is a constant distance between them. This is the upper case. This is lowercase. The distance between these two is 20. Give you two ASIC2 characters. You can do the subtraction. You can compare which one is larger. Why? Because in this table, the value of uppercase A is smaller than this uppercase E. So by comparing these two values, you can know the upper beta order of these two. And here you only have a 7-bit for each character. And of course, you can only represent 227, which is 128 characters, which is not enough for your test. Then we have the Unicode, which use more bits to represent more characters. We can also use some integer to RGB value to represent the RGB value of the image. We can also use some floating point to represent the song, or fixed point to represent the song. And these specialized instructions separated hardware by some hardware instruction set. For example, the ABX. Single instruction, multiple data instruction can help you to accelerate the processing of the image and processing of sound. So in this lecture, I briefly review the peaks, the number system, whose complement, and the basic operations, including arithmetic operations and logical operations. These are, I believe most of you has studied these in some undergraduate class. Any question? So no question, we can stop today. Thank you very much. Yes. One complement is intermediate result. The only goal you need that, but you need to complete it. It doesn't have to be one. No. And also, why yes, it's for this. Now, but when you use your compiler, it's high-level. Now, if you want to hire the complement, you prefer to write. Yeah, you prefer to even.